Lab 4 Oscillations. The purpose of this lab is to analyze the motion of an oscillating mass hanging by a spring and plot the energy changes of the system. The system in this scenario is the mass, the spring, and the gravity of the Earth, where there's nothing in the surroundings. The model could more accurately predict the x-coordinate of the position than the y-coordinate. So some key concepts are the energy principle, which states that the change in energy of the system is equal to the work of the surroundings plus the heat. This should be equal to 0 because there is no work in the surroundings for the system, including the spring and gravity of Earth. The total energy change is equal to the change in kinetic energy plus the change in spring potential energy plus the change in gravitational potential energy, which should be equal to 0. And you can see the formulas for each of the respective potential energy formulas below. Also related is Newton's second law, which says that the net force is equal to the change in momentum with respect to change in time. And the position and velocity update formulas are also used to update the position of velocity. So the initial conditions of this experiment. So the delta t in this scenario is 0.095 seconds. So every 0.095 seconds, the data is plotted. The initial position is negative 0.0292, 0.0238, 0. The object has a mass of 0.402 kilograms. The relaxed length of the spring is 0.123 meters. And the spring stiffness constant is 6.83 Newton meters. At each instance of time, the computational model calculates the net force acting on the object, which in this scenario is the spring force and the gravity, and then it updates the position and the velocity of the object. It also calculates the energy changes and plots the kinetic energy, gravitational potential energy, spring potential energy, and total energy for each instance in time. And then it would also plot the tracker data on the same graph to directly compare the two. So here you can see the actual code itself. So going to discuss the results. Here you can see that the total energy of the system is always 0, as you can see with that orange line, which is good. That's what we want. And you can also see that the spring potential energy and gravitational potential energy are oscillating back and forth, as long as the same thing with the kinetic energy, to make sure that the total energy is always equal to 0. Comparing the computational model to the actual experiment, the computational model does not necessarily do too well for the y position, but does for the x position. In blue, you can see what the model predicts versus in red what the actual experiment was. It is interesting that the actual experiment was way more clean than the model itself would have been, but that's okay. And same thing. Well, the y coordinate, it's very clean, but the model expects it to be way more negative in terms of going down further than it actually does. And what does it mean? The energy principle is satisfied as the total energy change of the system is always 0. So at any given moment in time, there is no change in energy, which means energy is conserved. And using the tracker data shown on slide 4, we can estimate that the period of oscillation is 2 seconds for the x-coordinate and 1.6 seconds for the y-coordinate, which is odd that there's that 0.4 second differential between the two. And the difference of these two quantities could be due to some air resistance or drag force, errors in tracking / videoing the motion, especially when it's going around in a circle, like clicking the exact center of mass every time was a little bit difficult, or the spring forces being stronger in a particular direction, and particularly the vertical direction, and making it go like faster in terms of when it completes its oscillation.